Yeah. Sure. All right. Happy to Greg. Just about atypical intersections, geometry handling.
Well, thanks for the introduction and for the invitation. So yeah, the plan was maybe to advertise some things that maybe were not super well known. So some link with these atypical intersections and some of the topics of the year, and some things that have something to do with dynamics. But maybe it was interesting since there are many people doing dynamics, and also there are many questions in this setting. So maybe what I want to advertise, so the bad slogan. The atypical intersections are everywhere.
They're quite typical.
Indeed, that's why it's a bad slogan. Yeah, indeed. So yeah, okay. So let's start with this introduction. And I will present two finiteness theorems. From two different worlds. And eventually, in the second part of the talk, I will try to explain to you why this atypical intersection, this Zilber pink viewpoint, kind of bridges between these two worlds and can let us recover both. Okay, so maybe the first setting is what people call the homogeneous setting. If I say something that's not so familiar, just stop me. I will actually be kind of informal. Okay, so we take S be a locally symmetric manifold. Of the form. So S will be denoted by S gamma. It will be something in the form xg mod gamma, where my xg is a symmetric space. Gamma is a lattice in G, so this is a finite volume manifold. Say in a simple Lie group. So you can think as xg, maybe the main example. Some examples to keep in mind are either the n-dimensional real hyperbolic space or the m-dimensional complex hyperbolic space or the Ziegel space. And many others. So it's something in the form like the connecting components of the real points modded out by a compact maximal subgroup. And the group is kind of a simple Lie group, like here will be SO1n, SU1n, SP2GR, and then there are many others. Okay, so it will be of non-compact type. I will not write it, but it will be the group. But the manifold can be compact. Very well. So maybe let's start with a remark. So what's a lattice? First of all, a lattice is just a discrete subgroup of the real points, or like of the group itself. And once we think that G comes equipped with with the probability measure, which is a hard measure, then the quotient G mod gamma, or equivalently, since here you're modding out by a compact subgroup, this quotient here, either G mod gamma or xg mod gamma, has finite volume for the induced hard measure that comes from the hard measure on the group. So yeah, the examples of lattices will be SL2Z, SP2GZ, and so on and so forth. But indeed, maybe let's start with a easy remark. So lattices always exist. So if you give me such a G, I can always find a group G. I can always find a lattice gamma. So maybe let's use Borel and Harishchandra. So how does it work? Well, somehow the idea that you take as gamma the integral points of the group. Of course, the true definition is a bit more complicated and lets you replace G by another group, a bigger one that's but differs by a compact sub, and then lets you take the integral points of that group. But somehow it doesn't matter. At this point, but the theorem says that there is always some Q form. You can always take the Z points morally, and then these guys here always have finite volume. So, for example, SNN, maybe an example to keep in mind, SNN that has finite volume. But for any end, say equal. Okay, and the question, so people call, once you give the opportune definition, people call these subgroups arithmetic subgroups. Or arithmetic lattices, so it doesn't really matter. And the question is, are there any others? So what's weird here is that the property of being a lattice seems to be an analytical one, a volume property somehow. But the property of being arithmetic seems to be an algebraic property. So you really have the integral points of some. But the answer is at least, it's easy yes, if you work in SL2. And I mean, this is really very much related to the theory of Riemann surfaces. So in some sense, I mean, if you fix the group, there are only countably many arithmetic subgroups, right? Because somehow you have integral, you have rational entries or entries in some Q-bar, in some algebraic closed field of cardinality, of countable cardinality. But in SL2R, of course, there are many lattices because you can find many Riemann surfaces. So there's a full, continuous, in the real sense, a discrete, continuous space of deformations for Riemann surfaces. So, okay, let's maybe remove SL2 from the game. So what else? Maybe SL2 is kind of special. And the other question is, the other piece of the question is, if I give you a lattice gamma, how do you decide whether it's arithmetic or not? So how whether gamma is arithmetic? A is just for arithmetic or non-arithmetic. So it seems, in principle, even if for a Riemann surface it's easy to construct examples, what if I just give you a Riemann surface? How would you decide whether gamma is arithmetic or not? Whether its fundamental group with this functional representation is arithmetic? And somehow you would like to do this by looking at the geometry of S. Of course, if I give you gamma, maybe you can try. Very well. Okay, so the first, maybe the most famous result is due to Margulis, Borlet, and Gromov, it's different papers. Gromov showing. And they prove that if gamma in G is non-arithmetic, then G has to be either of the form SO1N or SU1N. So X G will be, has to be either the real hyperbolic space or the complex hyperbolic space of dimension n. So, I mean, of course, it's up to isogeny. The groups is assumed to be simple, so somehow, I mean, there's a more general notion for irreducible lattices, and then you don't need to assume G simple, but okay. Let's ignore it for a moment. And so, first of all, Margulis proved that if G has a real rank bigger than 2, bigger or equal than 2, then gamma is arithmetic. Then there are 4 types of hyperbolic geometries, so SO1n, SU1m, SP1n, and F4 minus 20. And those 2 other series that don't appear here in real rank 1 were handled by Corlett in the Archimedean setting and Gromov shown in the non-Archimedean setting. But okay.
Sorry, so you can't summarize that as the real rank is at most is 1?
No, that's what I'm saying. So there are more groups in real rank 1.
Yeah.
So which are exactly SP1n.
And those don't have non-arithmetic groups.
And those don't have non-arithmetic groups.
Oh, okay.
And then the other one is F4. So F4 is like it's a complex group, but there's one specific real form, what people know about F4 minus 20, which is a real rank 1. It's an isolated one. And so there are 2 groups in real rank 1, for which every subgroup is known to be arithmetic, in fact, by the work of Corlett and Gromov shown.
Is there like a heuristic reason for that or intuition behind why those guys were left out?
I'm not sure. So SU1M is not so clear whether there exists a non-arithmetic lattices, so the list maybe is not so full. The idea for this superrigidity is that somehow you have kind of extra structures coming. So the softest group in some sense is SO1M. SU1M is slightly more rigid in some sense because also comes with a complex structure. So there's hyperbolic, this is just hyperbolic and complex. And here you have like kind of an hyperkähler structure almost. So you have hyperbolic, complex, but also these kind of extra structures. So the more special geometries you put in, the more kind of rigid behavior the manifolds seem to have. So in some sense, those 2, that's kind of the heuristic.
And for SU, they do all have non-arithmetic guys, right? You were saying most of them.
So for SO, they do. Yes. For SU, it's not known.
It's not known.
No.
Oh my God. Okay.
Yeah. So yeah, in practice, M would be, if you find a non-arithmetic lattice in G, and it's one of the known one, M would be either 1, 2, or 3.
Wow.
Otherwise you found a new one.
And those are all exceptional isomorphism other groups, right? SU1.
Well, SU11 is just SU2 in some sense, but SU12 is a 2 group. It's a different.
Okay.
Yeah. Thanks. Okay. That's just for reference. So there's one criterion that answers this question, which is the so-called Margulis commensurability criterion. That's the first result, that's the second one. And it says that gamma is arithmetic if and only if it has infinite index in its commensurator. So what's the commensurator of gamma? Just the set of points G in G, such that G gamma G minus 1 of G has finite index in both gamma and G gamma G minus 1. So that kind of, so if gamma was arithmetic, this group here will look like the rational points of G. But this also gives us, there's also a geometric implication. So, I mean, at the end of the day, we want to do something with atypical intersections. So, in this game, there's always a nice base. So the base is not a lattice, but the lattice maybe is the fundamental group of a nice base. So we want to, the game is to rewrite this kind of algebraic and group theoretic business in terms of this manifold, X, G, or gamma. So maybe we can have this object as like starting point of the theory. So how do we rephrase this thing in terms of S? So it has at least that if S contains one totally geodesic submanifold dimension bigger than 1, then it contains a dense set of such. But I mean, it's like when gamma is arithmetic. So why? Well, each element here gives us a non-trivial totally geodesic subvariety, totally geodesic submanifold inside S gamma cross S gamma. So those are, I mean, you can use this G to twist the diagonal embedding of S gamma into this product. And then you obtain non-trivial, you obtain true totally geodesic submanifolds, which are kind of modular correspondences. So they dominate in a nice way both factors. And you can use them once you find a totally geodesic submanifold in S gamma to pull it back and push forward to obtain new totally geodesic submanifolds, and they will like behave in a nice way in S gamma. And why I'm telling you this, because I mean, eventually we want to do a game with like special, with like, I mean, if S was a torus, like, or an abelian variety, the totally geodesic subvarieties are roughly they are the translate of the sub-abelian varieties. And there's a Zilber pin game for those totally geodesic submanifolds. And here, I mean, it looks like the totally geodesic submanifolds could play a similar role. So totally geodesic just means like smaller real or complex or HG embedded in an equivalent way. Any questions?
Is that a greater than 1 or a greater than or equal? It's total geodesic.
Greater than 1.
Greater than 1.
Yeah, but it's a real dimension. So real dimension 1, in fact, they always exist, and they kind of have a different behavior. So they are kind of they are always there and they are always there in the manifold. But what's really kind of exhibiting a more rigid behavior are the ones of real dimension 1, of real dimension bigger than 1. Real dimension 1, you should think of them as like CM points. Okay. So yeah, the question I wanna address is some sort of converse implication of this one. So in fact, there was a conjecture of McMullen and Reed, which says gives a partial converse to the previous observation. So what's the partial converse? Is that if S gamma contains infinitely many maximal totally geodesic submanifolds of real dimension bigger than 1, then gamma is arithmetic. And this is, I mean, well, it comes, the motivation also comes from the construction of Gromov and Piateschi-Shapiro of lattices in SO1n, so of non-arithmetic lattices in there. Okay, I will not get into that story. Very well. Well, so the theorem said the answer is yes. Theorem is true. The above conjecture is true, and yeah. So if X was the real hyperbolic space, this was done by Bader, Fisher, Miller, and Stoll. Well, maybe imagine. And yeah, if X was the complex space, then it's also yes by the same team of people, and also independently by myself and Emmanuel Ullmann. Everything happened in early 2020, and somehow, yeah, these proofs kind of show dynamical techniques, which are very interesting. And this proof I will explain in a moment uses these unlikely intersection things and theorems like H channels, which a priori don't seem to be fitting in the story. But so what's the difference between these two spaces? Well, in the first case, the quotient S gamma is not in general, it's not algebraic variety. For this case, S gamma is in fact an algebraic variety. And then you can use it as a base, and you can run this Hodge theory, and you can use the fact that at least you have an algebraic base.
So you're saying, I didn't quite follow, you're saying a priori, you know, as gamma is an algebraic variety?
No, I mean, I'm saying that
In the second case?
so, yeah. If you take H and with gamma any lattice in U1n,
Yep.
This is the complex guy.
Mhm.
This guy here has a unique algebraic structure.
Where does that come from?
Well, I mean, in some sense, it comes from, I mean, this is again Hermitian symmetric space. So it comes from, you can still define like the Bailey-Borel line boundary, it's going to be very ample. So in some sense, they're part of the theory. So if gamma was arithmetic, this is almost a Shimura variety.
Mm-hmm.
And in some sense, those proofs don't really use the gamma, at least in this specific case, don't really use the gamma as arithmetic, or not.
In this specific case, okay.
In this
So
specific,
that's not true for any Hermitian symmetric space, right? What you're saying is true here.
yeah, exactly. But in some sense, gamma is always going to be arithmetic. If you work outside, I mean, if you have like a Hermitian symmetric space and you model by gamma, the Hermitian symmetric space, I mean, the gamma usually is always arithmetic from the theorem over there, unless you're in this case. And in this case, the ball exhibits some special behaviors. Somehow, like the Bailey-Borel and the toroidal compactification are much more constrained. The Bailey-Borel compactification, you're just adding a bunch of points.
Yes, okay.
In some sense, that kind of proofs, they carry over.
Right.
Yeah, but think, I mean, even if gamma was compact, I mean, you need an argument, right? But the argument,
Well, then you have a negative curvature bundle.
yeah, exactly.
There,
Yeah, exactly.
Uh-huh.
Yeah, but then in non-compact case, compactification is not so great.
Yeah, okay.
But that's a good point. Yeah, and then you see also here maybe.
I'm not really sure you have unique that
Yeah, it's unique.
locally, but globally, I don't think it's known.
No, I think it's. Why? I think, I mean, you can
It's
extend.
not unknown that the complex structure is unique up to conjugation. So
No, you can extend Borel's theorem still works if you had the S is a algebraic structure and S1 another algebraic structure, the identity will be automatically an algebraic member.
No, but that Borel's theorem requires a complex structure, right?
you're assuming
It is a
the
complex structure.
complex structure is the nature one. That's what I'm saying.
Yeah, I mean,
I think
Not
you're saying,
just-
I think he's saying assuming the complex structure.
Assuming the complex structure is true, but
yeah, I mean, but that's like, yeah, okay. I mean, what I mean,
okay.
okay, I mean, for me, this is a complex manifold in a certain way. This is a
I mean,
Complex
taking
manifold.
complex quotient.
It's a complex manifold, and the group acts like in P1N and acts through the automorphism, and this is kind of living in Pn. And I want this action to be holomorphic. I want this action. I mean, so I take the complex quotient in the standard setting, and so this is kind of a God-given complex.
No, I just wanted to.
You agree?
And
I think we agree. I just wanted to underline that there might be another complex structure on that quotient, and then maybe
okay.
complex structure.
Yeah, okay. No, that's true. That's right. Yeah. But somehow when you do algebraic geometry, I mean, like once you're given this complex structure, I mean, you got that as a unique structure. Okay. Any more questions?
For calculation, there's also Margulis Mohammadi for. There's also this nice work of Margulis and Mohammadi for H3, I think.
Yeah, that's right. If M is 3 and the lattice is co-compact, it's also done by Margulis and Mohammadi. And also if gamma is Agromo, Piateschi, Shapiro, there's also work of Bader, Fischer, Miller, and Lafont. So there's like it's a long list. Yeah, that's right. Yeah. Thanks. Yeah. Okay. And maybe, but okay. Well, maybe just let me also say it in words. There's also another very interesting theorem of Philippe, Fischer, and Lowe that says that if you have a closed negatively curved Riemannian manifold, so no symmetric assumptions, if it has infinitely many totally geodesic hypersurfaces, then in fact will be an hyperbolic manifold. So in fact it will be of this shape. So it's even like you can give this kind of statements even outside, even without starting, which is quite kind of crazy, without starting in this set. So it's a very general thing.
You haven't explained the other two.
No, I won't. I will give another setting, and then I will give you these two final settings, and then I will explain the proof. But yeah, maybe let me just repeat it that if gamma is non-arithmetic, then there are only finitely many totally geodesic submanifolds. So that's the finiteness I was having there in the title. Let me give you the second setting, the non-homogeneous setting, and then I will explain the proof of this theorem. Okay, let me turn to the non-homogeneous setting. Okay, so what's we will work with translation surfaces. With just a pair x omega, where x is a Riemann surface, so just like x and and omega is a non-zero 1,4 on x. So yeah, just a pair, and there is a modular space of such objects. Which is just, in some sense, the total space of the Hodge bundle of MG. And yeah, and we can stratify it by counting the multiplicities of these zeros. So stratifies. So what does it mean? I mean, you take a vector k, so you denote it by k0, kn, such that, so it's a vector inside, it's made of natural numbers, such that the sum of the ki is equal to 2g minus 2. So in some sense, when g is 1, there's nothing to do, but in general there is. And then you can obtain, it's called omega mg kappa inside omega mg, and it's just the set of points x omega for which the zeros of omega are of this type, so counted with multiplicities. So there's like 1 0 multiplicity k0, another 0 multiplicity k1, another 0 multiplicity kn, and that's what this stratification gives. And the point is that they are all algebraic. But it's important to fix the type of multiplicity of the zeros. Yeah, and this is just the standard theorem that the multiplicity of the zeros of a one form is given by 2g minus 2. So maybe the question here is, what's the analog of totally geodesic submanifolds in the previous manifold S gamma, in this setting here, in omega mg kappa? So, I mean, this is in general not a homogeneous space, so we are kind of far away from the previous setting, maybe unless G is 1 or something. So what people look at is, so you can still, so the orbit closures we had before, they were kind of orbit closures. So there was a certain subgroups acting, and these orbit closures were kind of the totally geodesic submanifolds. And from that perspective, this can still be done. So there are still orbit closures, even though we are in a non-homogeneous setting. So where does the action come from? So GL2 R plus acts on omega mg kappa just in a smooth way, so in a very complicated way. So I will give you another perspective that doesn't require understanding this action, but I mean, if you've never seen it, it comes from the fact that the choice of a one form on X induces some sort of flat uniformization, and then you can see X omega as kind of a polygon with parallel sides inside a square, and then GL2R acts there. But I will give you also a perspective where you don't need it, so the orbit closures are, you will denote it by this curly and take any point x omega, you make this object act, and then you take the topological closures, and then you will get something inside omega mg kappa. You see that we introduce the stratification because if you take a point in x omega, I mean, this action will preserve the types of zeros on x and omega. So you will stay inside this bigger space. And yeah, that's like there's a subject called Teichmuller theory where people study these objects here. And before we had this condition of real dimension 1, and I'm going to tell you what's the analog of this real dimension 1 in this setting. But there's also a way to avoid it. So yeah, and we will work with strict orbit closures. Often for x omega, you will get the full space, but we care about the exceptional cases where this orbit is strictly continuous omega mg kappa. So there are two invariants. At least two invariants. One is called the rank of n, which is 1/2 of the dimension of the H1 of the tangent bundle of n. So what does it mean? So given x omega, so there's an exact sequence that is as follows. So there's the relative H1 of x with respect to the zeros of omega with coefficients in C. The maps to the absolute H1 of x, and the center, which is just somehow, the kernel, which is just denoted by W0, because it will be the weight one part. So that's just somehow the mixed structure when you do cohomology of the pair of x with respect to the zeros I mean, as base points, you take the zeros off of it. And then at the level, so this, when x and omega move on this space, there's a version for bundles of these things, so which will read h0, sorry, 0, h, omega w0, h1 relative, h1 absolute. This dimension just means that you take the tangent bundle of n and you project it down to the absolute part. So just the dimension of this projection. So you ignore the mixed part of this theory. And the degree of n is just the degree of the number field defining n. In H1 Okay, so that's both, I mean, to make sense of both theorems, to make sense of both things, there's a big level of technology hidden. So the thing I'm hiding is that this n, these orbic closures, they behave exactly as the totally geodesic submanifolds in the previous setting, in the sense that when you are like in a suitable covering of this space, it will be modeled around the H1 rel at some base point, and in those coordinates, it turns out that these orbic closures are linear. So in particular, it makes sense to consider these things as subbundles, and even more strongly, they are linear and defined or inside. They are kind of an open in some subvector space, so they are really defined over like a linear object and with entries in a number field. So it makes sense of just considering the degree as a level of complexity of this n to see the degree of the number field that you have in the game. And if you think about it, what happens when you take the compact dual embedding of xg? It's very similar that the totally geodesic subvarieties of a Shimura variety, they are kind of linear in those coordinates. And here it's completely the same. So it's quite surprising, and one wonders whether you can use similar techniques. Okay, and the theorem due to S field, right? Yeah, maybe I should have said that all this kind of linearity and all these properties are due to Esky, Mohammadi, Mirzakhani, and like in various sorts of, I mean, Wright and Philip and all those people. So the theorem is the following. So in each omega mg kappa, all but finitely many n, so I have rank 1 and degree at most 1, and degree at most 2. And yeah, with some theorem, with David Urbanic, we gave a new proof of the above. Using this channel and all this unlike intersection viewpoint. So let me give you first, before I tell you about the proof, let me give you a reformulation of this thing with avoids or closures, avoids rank and degree conditions. So maybe it's easier to digest that. Okay. So there's also the following theorem. So, I mean, theorem, let's say, the theorem over there is used as the key input also to obtain the following theorem of Wright. So now you work inside MGN, so the modular space of Riemann surface of genus G with n punctures, and you think this guy here, it keeps with the metric coming either from the Teichmuller metric, so or with the Kobayashi metric, they can always attach to any like complex manifold. I mean, in this case, it's truly a metric, so it's a hyperbolic manifold. And the theorem says that in here, there are only finitely many totally geodesic with respect to Kobayashi. Of complex dimension at least one. So what's the link? Well, an Orbi closure, so this space omega mg kappa projects down to mgn, where n is the same n you have here. So the punctures will be given by the zeros of omega. And the point is that the Orbi closures will project to objects that are totally geodesic for this Kobayashi metric, or intrinsically for the Teichmuller metric, so they use the same thing. And whatever this rank and degree condition are, the fact that you have some inequality like that will imply that you're just looking at objects that have complex dimension at least one. And before, I mean, and if you had the Boy quotient, the complex, I mean, so if you were working inside H and C or gamma, the totally geodesic submanifolds for the Kobayashi metric are once more the totally geodesic submanifolds that we were discussing before. And if you replace the complex dimension bigger than one by the real dimension bigger than one that we had there, in some sense, this theorem looks completely parallel to what we had in a Boy quotient. Because the Kobayashi metric is the symmetric metric in this case. Okay, so how to prove them? So where's the I mean, these things seem to be intrinsic, right? I mean, like this atypical intersection game is more like a sub-variety of a bigger variety, and there are intersections, and they can be atypical or typical. But this game looks completely intrinsic inside one space or the other. But are there any questions on the statements?
So you need this theorem of right as an input, or you also reprove that?
No, you reprove it. I mean, yeah. So what I'm saying is that this theorem of right is deduced by theorem one. Once you reprove theorem one, you reprove also this one. And the link is that somehow, if you had a totally geodesic subvariety T here, in some sense you can speak of omega T and kind of lift it inside omega mg. The opportunity kappa, and this omega t is an Orbi closure, and if it had complex dimension bigger than one, it's an Orbi closure of rank one and degree n. Or sorry, the other way around. And so there are only finitely many options. So what it shows, I mean, there's an argument hidden instead. So if you can control these guys here, you control T, and the fact that the Kobayashi geodesics are related to Orbi closures. But in some sense, yeah, I wouldn't say we reprove it, but you reprove one of the main inputs. It's more fair to say. Okay, maybe in 20 minutes, so okay. Idea of the proof. Well, let's do first the complex hyperbolic setting. But let me say, I mean, I won't have time today to describe this setting, but let me say that in some sense, this setting here is not predicted by this Zilber ping conjecture. So there is a VHS induced by these things. But the fact that you keep also this omega in the game, it's not quite the standard period domain, period mapping games. So that's kind of something different from the standard setting going on, apart from the fact that it's intrinsic. It's also something like deeper than just Zilber ping for this mixed VHS game. Okay. So let's see, let's focus first on the idea. So how would you come up with? So you have gamma, let's recall that you have gamma lattice in P1n. Oh, and maybe bigger than one. And those are, so inside the manifold, so we said that this guy here is a complex algebraic variety, even smooth. Oh, maybe if you want to be precise, you will assume that gamma is torsion free, but even more than that, actually. And so this is a real algebraic group, but in fact, it turns out that gamma. So the first observation is that gamma has entries in OK, the ring of integers of a totally real number field K. So what do you mean by that? Actually, this is not so bad. It means that if you take Z and you add the traces under the joint representation of gamma, for all gamma in gamma, this guy here is going to be exactly equal to O. It's not quite true that it has entries in gamma, it's just that you can make it so that.
Probably not exactly okay.
Sorry?
Probably some subring of okay, right? There's no way you can make it be actually okay. Take a congruent subgroup, it's not going to be okay. It would be like Z plus M okay or something.
Yeah, that's right. But okay, that's right. That's right. But I mean, I also want to impose that K is really the smallest field. So nevertheless, I want to say that also K. I will pick K in the sense that if I do Q the same thing, it's K.
Yeah, it can be a finite index thing in there, I think.
Yeah, no, fair enough. Yeah.
But how far is this from being just conjugatable to having entries in okay?
Yeah, indeed. Yeah. Yeah, that's exactly part of the strategy. So in fact, gamma is the risky. So I mean, this means, so let's forget about OK for a moment. Let's focus first on K. So this thing here is that the adjoint trace field of gamma is a totally real number field K. And the fact that gamma is a risky density in T, and is a Basser theory, tells you that up to passing through a finite index subgroup, and conjugation, and real conjugation, you do obtain G bar, so a K form of G. So this is my real group P1N. This is with the bar, it's kind of some K form, such that gamma lies in G, okay. And in fact, that's crucial. So we can call this guy, let's call it just A of gamma. So we can call this guy, so in some sense, the arithmetic approximation. So I will give first kind of a sketch of the idea rather than just focusing on how to make it truly rigorous. So let's call it the arithmetic. Maybe we call it the arithmetic approximation of gamma. So in some sense, if gamma was arithmetic, you would like to say that gamma is almost this G of K, and K was very small. So you can measure how far S gamma is from an arithmetic quotient. By considering also the arithmetic approximation of S gamma. So what's that? So the arithmetic approximation of S gamma, if this guy here is the arithmetic approximation of S gamma, the arithmetic approximation of S gamma should be something like x plus x plus x, so degree of k over q times modded out by g of OK. So now g of OK in general is not a lattice. It's not a lattice in G. It's more like it doesn't tend to be discrete, right? But nevertheless, if you index the embeddings of K into Q, I mean, it will act, G of K can act on this space. So we're like gamma acts on the first component by using the first embedding into the real points of the group. And then it acts on the second one using the second embedding, and so on and so forth. And this guy, you would like to think that there's a map from S gamma to this thing. And somehow the bigger this space is, the further away from S gamma you are. The further away from the arithmetic setting you are. But now what happens if we do the same game once more with a totally geodesic submanifold? So the totally geodesic submanifolds are precisely the ones for which you can redo the same game. So a totally geodesic submanifold Y is itself of the form H. So before we had, so this xg was just Hn, right? So now we have an Hm mod gamma y with m 3 is smaller than n and bigger equal than 1. And we can also speak, and again, it's a complex hyperbolic space, modular lattice, now in P1M. So that's roughly what, I mean, it's slightly more complicated than that, but that's roughly what totally geodesic submanifolds are. And now you can think of reapplying the same game and consider the arithmetic approximation of gamma, which will be some sort of HMC times HMC. Modulo some group like H, okay. And if you believe in some functoriality, maybe this guy will map in here. And then now we are kind of realizing why, so morally, why is S gamma got the arithmetic approximation of Y, everything happening inside the arithmetic approximation of S gamma. And so what's the idea? And now, I mean, so what I'm hiding is like, in which category am I doing these kind of objects? So if you were just in some sort of too soft category, there's no reason why atypical intersections should be strong. But what's the idea to finish this proof? So the idea is that gamma non-arithmetic implies that the codimension of S gamma in the arithmetic approximation of S gamma is big. It's bigger than 0. And this fact implies that totally geodesic submanifolds are unlikely intersections, are atypical intersections. Also of positive dimension. But of course, here it's not quite a Hodge theoretic setting. It's just, I mean, you can form this space and maybe you do have a continuous map, but it's a very soft setting. But let me just explain why they should look in intersections. So let's show where the typicality come from in one example. And then I will tell you the precise setting. So what's the first example where you can run this theory? Is that when n is 2, m is 1, and the trace field has degree 2. So you have a complex hyperbolic. You have a Ball quotient of dimension 2, a totally geodesic curve, a totally geodesic hypersurface, and the trace field has degree 2. So in this case, so we said that d mass gamma is 2, dim y is 1. And what are the dimensions of these objects? Well, the dimension of the arithmetic approximation of S gamma should be 4 if gamma is non-arithmetic. So let's say it's either, let's assume for simplicity, it's either 2 or 4, depending on whether gamma is arithmetic or gamma is non-arithmetic. It looks of dimension 2 because you would like to say that it's like it's of the form h2 plus h2 modulo something. And this guy has complex dimension 2, and the other copy is complex dimension 2. So 2, it's like this one times this one. But now, what's the dimension of the arithmetic approximation of y? Well, you would think that you do the same trick, but now you do it on something that will look like h plus h modulo something. So this guy looks like it has dimension 2. So if gamma is non-arithmetic, you're in a 4-dimension. You're intersecting two surfaces. All right, you're intersecting this one and this one. So you're intersecting a 2-dimensional object and another 2-dimensional object in a 4-dimensional space. But the intersection turns out to be 1 dimension. So if you can run this argument, and you believe me that y is equal to s of a y inside a y, there is an excess of dimension. So the expected dimension would have been 0 because you're intersecting two-dimensional objects. So it turns out to be an atypical. So it is an atypical intersection. But in which sense? So the question, I mean, that looks like kind of, I mean, more than an idea, maybe it's more a heuristic. So that's like, okay, what if you can make this argument work? But the question is, how do we make it work? But are there any questions on the setup?
Wait, you said if gamma is arithmetic, then the degree is 1, right?
Well, it's more complicated now.
So why can this arithmetic approximation of y be only 2-dimensional? It could be 1-dimensional.
Yeah, that's right. That's good. Yeah, that's right. So there are two problems. Like, I mean, sometimes the trace field is bigger when you use these compact factors. So in some sense, what you are measuring is like. So you should consider the k form of G, tensor it over k with the values embedding against the real points. And the gamma is arithmetic if all but one of those guys is compact. And then some of this compact business disappear when you do this arithmetic approximation. That's one thing, but you're right that, I mean, if y was of the form h mod gamma y, and this gamma y itself was arithmetic, then in that case, this guy here would have had dimension 1. But then it's even worse, because now I'm intersecting a 2-dimensional object, a 1-dimensional object, in a 4-dimensional space, and I get a 1-dimensional object. So it's even more atypical. But you're right in some sense. I mean, but I'm lying in many places, but that was a lie as well. Yeah. Thanks for that. Yeah. Okay, so in 2 minutes, how do you make it work? So yeah, the key point is that H1 gamma. So gamma is the fundamental group of S gamma. So maybe let them try. The key point is that H1 phi 1 of S, the adjoint representation of rho. So let me call rho, if you want, the map from gamma, just the inclusion from gamma to P1n. So I want to say, work in the case where n is bigger than 1. I want to say that this representation is essentially a local system, and in fact it is a complex VHS. So the space Hg is just the kind of the moduli space of Hodge structure of complex of Hodge structure of signature 1n. So there's kind of a theory like that. So it has a complex. It is a VHS, but it's even stronger than that somehow. It exhibits, as long as n is bigger than 1, a strong rigidity property. And this rigidity property implies that this H1 vanishes also when you twist rho by the values embedding of sigma from K to Q, from K to R. So you obtain new representations inside G sigma. So that was the group I was introducing here. So from a big trace field, I build a lot of local systems just by conjugating by sigma the standard ones they have. But this changes completely the thing, and a priori it's not even a VHS. But the fact that the rigidity is preserved, it gives me that also these guys are VHSs themselves, because they are rigid local systems. So that's some sort of non-abelian Hodge theory. And it tells me that when I put all of them together, all this local system rho sigma they have here, this guy here, it turns out that forms a QVHS. And in fact, if you use enough, if you leverage a lot this vanishing, which is done by many people, and if you combine it with work of Hainaut Grofnik, in fact, it's a ZVHS. And so we can denote it by V. And the idea is that this map here, once you understand the opportunity, so it's a little bit more complicated, but the way to formalize this piece of the diagram is to work with the period map associated to V. And then, once you do this diagram kind of works. And then your atypical intersections, you can make it format for S gamma, for the pair S gamma V. This is ZVHS here. So it's a ZVHS that you constructed, that you have to construct exactly to make this strategy work, and it uses this kind of non-abelian Hodge theory to make it work. But once you have this, then you can run, the so-called geometric Zilber ping. For this VHS here. That tells us that somehow there are only finitely many maximal atypical intersections. So in particular, there are only finitely many maximal totally geodesic submanifolds. And then we stop here.
All right, great. Any questions?
So how do you get the rigidity there for all places?
Yeah, I mean, it's so first is a theorem of Garland, Raghunathan, Selberg, many other people that you have this vanishing of this H1, Prasad as well. So well, it changes whether this guy is compact or not. But okay. So this one vanishes as soon as you have any lattice in P1n for n bigger than 1. So when n is 1, it's not 2. And then you want to try to twist and see the new twisted representation. So just to be clear, I mean, this map sends gamma is inside GK, and then it sends it roughly to sigma of gamma, where sigma is some place of K. Now you wonder, is this a 0 or not? Well, this is kind of the tangent space of a character variety. In twisting, you can think of that. This one is kind of similar to the H1 by 1 of S, add row. But then it is a complex, but I mean, it comes with extra structure, but you can kind of take the conjugation by sigma outside here and make it on the H1 so much. So it's like H1 tensor with C, I mean, along sigma. So you can make sense of this. And the fact that this one vanishes means that also the other one vanishes. It's kind of a homological, I mean, the fact that it's a homological criterion will not depend on the sigma you pick.
Okay, because you use cohomological rigidity and
Yeah.
rigidity.
That's right.
I see.
So yeah, I mean, maybe I didn't explain well, but you recover all the other H1 add rho sigma from this one, from the one without sigma, and then by tensor with sigma outside. So if one vanishes, all the other ones vanish. So in some sense, you don't need to prove. But morally, so this rigidity implies that the local, I mean, conjecturally, would imply that this local system comes from geometry. And if it comes from geometry, there exists a ZBHS. That's like, I'm just constructing the ZBHS that should that should give the geometricity. So geometric means like a slice of a true family, but there is a family somewhere. And that family gives a ZBHS. And that's kind of, you should think that ZBHS. And in fact, I mean, concretely, lattices are constructing this.
You're using like a non-grossing results.
That's right, yeah. But in fact, you don't need it, yeah.
Oh, you don't?
Yeah. So it makes life easier, but there are even two ways to avoid it, but just to prove this theorem. So to prove the finite.
But you can get the VHS without their work, the QVHS?
So you can get the QVHS, yes, without the work.
Oh, really?
But you don't get the ZVHS. And then you not like to use action a priori, you needed the ZVHS.
Yeah.
Now there was also more freedom then.
That's okay.
But also in this setting, if you have infinitely many totally geodesic submanifolds, there's a way to prove the integrality by yourself without using the kind of machinery.
How do you get the positivity for the QVHS?
I mean, and sometimes it's hidden. I mean, you don't need from the rigidity you get a VHS.
From the rigidity alone, you get a VHS. Oh, yes. Okay.
But then you get a VHS on every single thing.
Yeah, I see.
And then you have to glue the VHSs. So you have all the positivities slice-wise. But then the question is like, do you have to massage the polarization at each single factor to make it kind of a polarization? So it's kind of running a super high-tech value restriction.
Sure.
But the positivity itself comes from like a non-abelian Hodge theory. I mean, it's like correlative, the rigid implies. So you don't quite need to do. But the fact the first one is a VHS, it's kind of given. The other ones, it's not so good. Indeed, yeah, you see, here I'm cheating because it's not clear whether I will still keep a Hermitian symmetric space. When I put the VHS structure on this rho sigma, I don't know what I get. So I don't even know what the monoderm is. Not a PU1, it could be something else. I have no idea what kind of Hodge diamond I could see. So here it's much more complicated. So it's not, so you really need ZVHSs. Like the Shimura setting is not enough. So you should, this is not a Shimura variety. Because you don't know what you have no idea what kind of Hodge diamond.
Yeah.
It's totally random.
Other questions?
The proof for MG has a similar flavor.
Yeah, the proof for MG, it's kind of a similar flavor, yes. So you will realize once more, you will interpret the rank degree conditions, but you will work somehow in some sort of Hodge bundle above a mixed Shimura variety, and you will realize orbic closures as like intersections of omega mg kappa with something else. And this something else is kind of a mixed subsimilar variety, but it also kind of have another automorphic direction. It will have some sort of one-form direction. And then these rank degree conditions will show that, will imply that this thing is an atypical intersection. But then you have to prove, then it will not be implied by a geometric Zilber pink, not even the mixed one, because there's a new behavior that's kind of hidden in this one-form contribution. So it's kind of a Zilber pink in some automorphic band, which is beyond the mixed. That's right. And then, yeah, you have to, but then the way you prove it is, yeah, if we have another do we have another lecture? Okay. Yeah, and then we can pick the topic. But I mean, the idea was to prove, to show this proof of the geometric Zilber pink conjecture in one set. So
So just to understand, how much this proof requires P1n? So in particular, like this conclusion that the traces are in the real number field, or any kind of number field. You get it from a lattice in P1n. Do you have it also in O1? Do you have it in F4? Like, where does it break down? That's some sort of local rigidity, right? That you're using.
Yeah.
How general is that?
yeah, it's this local rigidity
Yeah,
is always true. I mean,
always true.
yeah,
Except for SL2, it's always true.
yeah, and also for SL2C maybe.
Okay.
Okay, but never, it's always true. But the problem is that I don't know what to do with this rigidity unless the base here was a complex variety.
Yes.
Because in that case, I can run this Hodge theory business. But without knowing that this guy here is kind of a Kähler manifold, I don't know what to do out of this. So it's kind of, this is always there.
But okay, let's go to the Hermitian symmetric setting, for example.
Yeah, but then I know already that everything is arithmetic, right?
Well, not always, not in all the cases, right? You have,
But all the cases apart from SU1N.
oh, I see. The other cases aren't Hermitian symmetric domains. They're just, I see. Oh, so the only Shimura variety with real rank 1 is SU1N?
Exactly.
I see. Okay, I understand.
That's what kind of
Started this.
yeah. So yeah, SP1N, for example. I mean, okay, you already know it's arithmetic, but nevertheless, I mean, you don't have a quotient by the complex maximum. You won't have a complex structure.
Yeah.
You cannot run like.
Okay. I see. I understand.
But there is a general. I mean, I can tell you there is a more general setting where you can make a statement.
Okay, maybe for time, we'll stop here and thank Greg again.